Hello? Okay, okay. Hello everyone, thanks for coming to Astronomy on Tap, our third Astronomy on Tap. For the people that were not here for the first two events, Astronomy on Tap are short talks about astronomy for not astronomers. My name is Stefano, I'm a professor at UC Davis, and with me there is Victoria. She's a graduate student at UC Davis that now will tell you how the night is structured.
Okay, I see a lot of you look familiar, so it looks like you guys have been here before. But I'll go through the schedule again, just in case. Basically, what we're going to do is hear from two speakers, Dr. Tomzcak and Rachael Livermore. They're going to tell you about how many stars are in the universe and searching for the dawn of galaxies. The first talk will be from Adam, and if you've been here before, you know this, but the way that we handle questions is instead of just getting you guys to raise hands and me picking you, I'm going to have you text this phone number so that I can choose the best questions. The phone number's up here, but it's also posted around the room, and you can ask anybody with a name tag on, and me, because I don't have my name tag on, what it is. So when that's over, we will have a Q&A, and then after the Q&A is over, Stefano and I will tell you about some cool news that's been happening in astronomy this month. You should pay attention to that because the trivia, which is happening during the break, is going to be based on that. So your incentive to ask a question is that if I choose your question, I'll send you a little star emoji back, and you can pick up a prize from Isaiah back at the prize table. He's waving. You can get a sticker or a pencil or something. And right, so during the break, we have two things going on. You can play the trivia, which is, again, based on the news, so make sure you pay attention. If you win trivia, you can choose this really cool 30-meter telescope mug or a Chewbacca mask. The Chewbacca mask makes noise and talks when you move your mouth, so yeah. What's also going on is the raffle. So our raffle here will make, again, as usual, more sense when you hear the astronomy and the news. But the options are Hayabusa 2, which is a Japanese space mission, or Grace FO, which is a climate experiment. You can vote for your favorite with a donation and get a raffle ticket. Choose your favorite raffle bucket there in the back. At the end of the show, whichever one has the most raffle tickets, we'll choose a winner from, and that person will win a Galileoscope. After the break is over, we'll come back and we'll hear from Dr. Rachael Livermore, who's sitting here in the front with Adam, and we'll handle questions the same way. And when her talk is over, we'll announce the raffle and trivia winners, and everything. It will be over. Okay.
Awesome.
Okay, so now we're going to hear from Adam, who's a postdoc at UC Davis, and he's going to tell us about how many stars are there in the universe.
All right, thank you. I'm really excited to be here and speak in front of everybody. Okay, so what has always fascinated me about astronomy is the sheer vastness of the universe and how mind-boggling it can be. And I don't think that I'm alone in that viewpoint. And since my research is heavily centered on studying the stellar mass assembly in galaxies throughout the universe, I thought I would be pretty apt to try to answer this question for everybody. How many stars exist in the universe? So before I dive into my talk, I want to explore this little fun, whoops. How do I can just exit this. So I have this little interactive internet web tool which can allow you to explore the universe in real time if this loads. Oh no. All right. It seems to be a slow internet connection right here, so I'll just jump right back into the talk and maybe we can look at it at the end. Okay. But anyway, so what I have shown here, sorry. So what I have shown here is a view of the distant universe. It is a chunk of a galaxy survey called the Cosmos Galaxy Survey. And the size of this field is about 1/7 the size of the full moon. So it's a really tiny area on the sky, but you can already see it's littered with thousands and thousands of galaxies. And this is how we peer into the distant universe and try to get a glimpse of the wide variety of galaxies that exist out there. But before we talk about the galaxy population as a whole, we need to consider galaxies individually. So right here I have an example of M81, also known as Bode's galaxy. This is a nearby galaxy that we can get a very detailed look at. In fact, I have a scale bar here which shows 100,000 light years, just to give you a sense of it. So within galaxies, there are constituent components known as star clusters, which I have an example of shown here. Now, this is not a star cluster located within this galaxy itself. It's actually a star cluster known as Omega Centauri, located within our own galaxy. And this allows us to get a really detailed look at it. So if we take an even closer look at it, and this is an image from the Hubble Space Telescope, you can start to see individual stars with great detail. Now, the first two fundamental observables of stars in a cluster such as this are, one, their luminosity, bright and faint, and two, their color. You can see red and blue stars here. So it makes sense to just naively go ahead and plot these two properties against one another in what astronomers call a color magnitude diagram. So here I have, oops. I need to get used to that. Actually, okay. So here I have that plotted. So luminosity is on the y-axis. You have bright galaxies at the top, or bright stars at the top, faint stars at the bottom, and on the x-axis is the color: blue on the left, red on the right. And you can see that this is this is not a random risk distribution. It forms some coherent structure which gives us information about the population of the stars and how old they are and other details. So this color magnitude diagram shown in this more explicative rendition on the right sort of breaks up into various components that I want to break down for you here. Okay, so when stars are born, they form in primarily one of these main classes of stars, which really pertains to their surface temperature. These larger, bluer stars are the hot ones, and that's why they appear blue in color. The smaller, fainter ones are cooler, and that's why they appear redder in color. And this, just for reference, this G-class star at the bottom here, that's the type of star that our sun is. So just to give you a scale of where we stand in this pantheon of stars. Okay, the nice thing about this is we can look at this spectra of these stars, their brightness as a function of the wavelength of light that they emit. And they're very characteristic. So that big O-class star has a spectrum of this shape, whereas the M-class star way at the other end has a spectrum of this shape. And these constituent components are what make up a galaxy, and being able to break them down in this way allows us to start to come up with some theoretical construct as to the light profile that galaxies should produce. Okay, so let's start to build our own stellar population here. So here I have a lineup of those various classes of stars that I just showed. Now, when the stars form, you don't just get a one-to-one correspondence as a function of class. In fact, you actually get a lot more lower mass stars for every high mass star that you form. So this distribution will look something like this. And this has actually been measured by astronomers that have actually just gone to nearby star clusters and counted up stars as a function of their mass. And so if you just count up how many stars there are as a function of their mass, you can see that there are a few high mass stars and tons of lower mass stars. And there is some functional form to this which we can use as a prior or some information when we're trying to construct a theoretical stellar population. All right, moving onward. So this represents a stellar population that has just formed. And such a population falls along a very tight sequence in that color magnitude diagram known as the main sequence, shown right here. Now, if we give it a little bit of time, the first thing that'll happen is that the most massive stars will explode in these very large displays known as supernovae, effectively wiping them out. And so that will destroy this upper left part of the main sequence. So those stars are gone. With some more time, the next highest mass star will enter a new phase known as the red giant phase. And that'll populate this upper right portion of the diagram. As we push on forward, these red giants will next evolve into what are known as white dwarfs. So their exteriors will be shed off, and you'll be left with only their central, extremely hot core, which makes them appear much hotter, but also much fainter. And so these remnants will be populated in the lower left portion of this diagram. And as more time goes on, the next highest mass star turns into red giants, and you sort of go through this cycle again, filling out this color magnitude space here. Okay, so that's our single stellar population at the moment. But galaxies aren't just single stellar populations in of themselves. They can form stellar populations whenever they want to. So when you look at a galaxy, you can have some young stellar populations, which will be dominated by bright bluer stars, and older stellar populations, which will be dominated by bright red stars. And various proportions of these will inform the light profile that a galaxy eventually produces. So when you combine this all together, you get a galaxy. So we've successfully created our galaxy right here. Again, this is M81. And now that we have an observed galaxy, or if you go to an observed galaxy, you can actually look at its light profile. So let's say we look at this galaxy and it has this light profile here. We can go to our theory of stellar populations and look at a wide array of them. So basically, astronomers produce various thousands to thousands of various stellar populations with different proportions of young and old stars, and look at the theoretical light profile that they produce. And then we go one by one, comparing each of these light profiles from the theoretical or synthetic model and compare it to what we observe. And we basically just pick out whichever one looks the best. And there are statistical methods for assessing how reliable this is, and we found that it's actually a very good method for estimating the mass of a galaxy. All right, so moving on, now we don't just have one galaxy in the universe, we have tons and tons of them, as exemplified in this image right here. But now, even though this image appears as just a two-dimensional projection, it really represents a three-dimensional space. So let's sort of look at it that way. So if you think of that image, this chunk of space as this three-dimensional volume that I've drawn here, with us observers in the lower left corner, this portion of the space would be the nearby universe, and this portion of the space would be the distant universe. And what's important is that light has a finite travel speed, and so the more distant galaxies, the light that they emit will take a longer time to reach us. So we will be observing the distant universe as it was much younger than the nearby universe. And this is an important caveat when studying galaxy evolution, and I'll get into that in a few more slides. Okay, so what we can do from here is break up this volume into these various segments and look at each segment separately. So let's focus on this one segment right here. Within this segment, there will be however many galaxies there may be, and what we can do is count them up as a function of their stellar mass. So an example of that is shown in this right diagram here, where you can see a large number of low stellar mass galaxies, and I've scaled this to the mass of the Milky Way. So the Milky Way galaxies of the class of the Milky Way are numerous at this sort of level. Less massive galaxies are more numerous. More massive galaxies are less numerous. And we can characterize this, and by adding up all of the stellar mass that we see here, we can get a sense of how much stellar mass exists in the universe in this one slab of space that we have constructed. We can repeat this process for all of those other slabs for the nearby universe, the more distant universe, and the even more distant universe, and count up the total amount of stellar mass that exists in each slab on its own. And as I mentioned, because the more distant universe, the photons take longer to reach us, we're actually looking at an earlier phase of the universe then. So if we plot up the total amount of stellar mass that we observe as a function of the age of the universe that these slabs represent, then this is the diagram that you would see right here. So here we have the stellar mass divided by the volume of each slab so that it's on a consistent basis. And you can sort of see this growth of stellar material over cosmic history. So if we go to, say, a time that is half of the age of the universe, so the age of the universe is about 13.7 billion years currently. So if we go to half of that age, like 7 billion years or so, we can see that only about a quarter of the stellar mass has been formed relative to the present day universe. Now, this makes it a little tricky to estimate the total number of stars in the universe because what we see in the more distant universe has yet to evolve into the present day time. So it's really tricky to make extrapolations off of that. But, but if we just assume that the average applies across the entire cosmos, so we take the average stellar mass density, say when the universe was half of its current age, right there, and assume that the full cosmic volume of the universe is populated with this average mass density, then we can estimate the total number of stars in the universe. Now, I won't, does anybody want to venture a guess? Yes? We have 42. Does anybody want to say higher or lower? We got a higher. Okay. When we do this exercise, we wind up with this number of mass. So I actually had to Google how to pronounce this number, and it is quintillion. So 553 quintillion, so on and so forth, suns of stellar mass. And again, this is only approximate because, as I showed in an earlier slide, stars come in various range of masses. So it's hard to exactly say the total number of stars from the stellar material that you estimate. Okay, so that concludes my talk. So I've included a link and a QR code that could take you to the website that I failed to show you earlier on. But let's see if it has now had time to load so we can see what there is. And indeed you do see it. So this, as I mentioned, is an interactive tool where you can zoom in and explore around. So every point, almost every point you see in this image, yikes, is a galaxy in the distant universe. And you can actually click on them in order to get some details on them. So most of these are written in astronomy units, so you may not understand some of them. But it's really a blast to just zoom around and explore around and see what there are, because this is real data. This is what astronomers such as myself actually use to study the universe. All right, thank you.
You hold that.
Oh, okay, I hold this.
Thanks, Adam, for the nice talk. Okay, first question from the audience. Why are old stars so much larger than young stars?
So there, why are I presume that they're asking why are so many stars more larger than our sun, and that is because if you think about it in a statistical sense, if you look back to that slide where I showed you how many stars of various mass form, and there were a bunch of low mass stars and fewer high mass stars. If you were to pick at random one of the stars, you would more likely pick a lower mass star than a higher mass star. And so in a sense, it's really just statistics.
Why do you use the wavelengths that you do to classify stars? Why not use X-ray or some other wavelength?
Yeah, as it turns out, optical light is really where a lot of stellar emission comes out in. Now, there are some stars that do emit in a lot of their light in the ultraviolet, and some more so in the infrared. So those wavelengths of light are important as well. But at X-rays, individual stars don't tend to produce X-ray photons because those are such high energy photons that don't tend to be what comes out of a star's photosphere.
Okay, last question. Can you estimate the age of a distant galaxy where individual star cannot be resolved by combining spectra it gives off?
Good question, and that is in fact what we do. A lot of astronomers will look at the spectrum of a distant galaxy, and you won't be able to resolve individual stars at all. In fact, for the vast majority of galaxies in the universe, you will not be able to resolve individual stars. So really, when you take a spectrum or any observation, you get everything all at once, all the stars all at once. But there are still characteristic features in a galaxy spectrum that can tip you off as to the average age of that galaxy.
That's great, thank you. Let's thank Adam one more time. Thank you. So I got 5 questions while we were asking Adam questions. So if you have more questions for him, he will be here. He'll be around. So definitely come ask him other stuff.
Okay, astronomy in the news.
Okay, so our first astronomy in the news this month is a very pretty picture from Hubble Space Telescope that shows an example of a gravitationally lensed spiral galaxy that's being lensed by a small cluster of galaxies. Now, to really do any justice to gravitational lensing, it needs its own Astronomy on Tap presentation. And I have a feeling Rachael might mention this in her talk. And if you come back in October, our speaker in October will do an entire presentation on it. But the short version, and so in the same way that gravity pulls mass together, it also bends light. And so the faraway object, if it's affected by a mass in between it and us, can actually be magnified and stretched, and often we see it more than once, as in this example. So in this pretty picture I was just showing you, the cluster is the lens, so it's doing the lensing. It's the little circular yellow objects here, and the spiral galaxy is the faraway thing, and that's the stretched out orange and blue shapes here. So we can see this object maybe at least 4 times here. And the reason this picture was even taken is that one of Stefano's friends was looking for supernova, and a supernova went off in this lensed spiral galaxy here, and it triggered Hubble Space Telescope to take a picture of it. And so we have this nice, resolved, pretty picture of a lensed spiral galaxy now.
Okay, second news for today is about the Cassini Mission. You probably heard about this. This was a satellite that was going, studying Saturn and the moon of Saturn for several years. This is Enceladus, is one of the moon of Saturn. This was the picture of the day in July 1st. And so even though Cassini mission finished and the satellite burned in the atmosphere of Saturn, we are still analyzing data. And so recently there was a nice... recently there was a Nature paper about some results from Cassini. We have a video here telling about this cool result.
Scientists have learned a lot about Saturn's frozen moon thanks to data from NASA's Cassini spacecraft. In 2015, the spacecraft uncovered warm cracks, spewing ice grains and vapor into space. Researchers also discovered that a massive ocean is hidden beneath the moon's icy crust. Cassini ended its mission by deliberately diving through Saturn's atmosphere last fall, but scientists have continued to study the wealth of data from the dead orbiter. In a new study, scientists found large carbon-rich molecules in ice grains ejected from Saturn's sixth largest moon. Whether these complex molecules are lifeless elements or a possible clue that microbes are living below the moon's icy crust or once did remains to be seen. For now, Enceladus seems to have the right stuff for life as we know it. As Dr. Klein said in his statement, with complex organic molecules emanating from its liquid water ocean, this moon is the only body besides Earth known to simultaneously satisfy all of the basic requirements for life as we know it.
So we already knew about the geyser coming out from Enceladus. The new result is that actually the material that is coming out is this very complex molecular, and so that are really consistent with having life or having the possibility to have life in this ocean that is inside Enceladus.
So also this month, at the end of June, the Japanese spacecraft Hayabusa 2 approached the asteroid called Ryugu. And you might have seen this picture in the news a lot. I saw this a lot this month. This is a collection of images that the spacecraft sent back to us of the asteroid as it got closer and closer. And what I saw mostly being reported was that the shape of the asteroid is weird. It's kind of cubical or looks like a diamond or something, which is a little bit strange. But actually the mission is way cooler than just that. So to give you some overview, Hayabusa started orbiting Earth in 2014, and it followed Earth around. Sorry, it started orbiting the Sun in 2014 with Earth, and it orbited around a few times with Earth to get enough momentum. And then in 2016, it started orbiting Ryugu, which is in the green here, following Ryugu. It doesn't just follow Ryugu, though. It got really close, so it ended up getting about 60 meters away from Ryugu. And the point of this whole mission is to study the composition of an asteroid. So the way that it's doing this is it has 4 little landers in the spacecraft that it's going to drop onto the surface of Ryugu. This is the most adorable part of the mission. So the landers are not like Mars rovers like you think. They're not going to roll around because the asteroid is pretty small. They're just little boxes, kind of. And so if they need to move, the way that they move is not by rolling. It's by these internal weights that are inside of them. And so they sort of flop around with the internal weights in them, which I think is really cute. And the best part of the mission is that one of the lander's jobs is to detonate a bomb and create a crater on this asteroid in order to study the composition of the material that's underneath the surface of Ryugu. Now, of course, the spacecraft doesn't want to actually be in the way during the explosion, so it's going to go to the other side of the asteroid and sort of hide and take cover. And the explosion happens, the spacecraft comes back, and then there's all sorts of material in the air, so it'll come down and collect some of this material that used to be under the surface of the asteroid. Once it has that, it'll put it in a capsule, come back to Earth, and send the capsule back down through the atmosphere of Earth. This capsule will land somewhere in Australia, and some scientist somewhere is going to be able to touch and feel and look at the innards of an asteroid, which is amazing. It's amazing in its own right, but also it's really cool because this lets us learn about the origins of the solar system. So that's because we know that the planets in the solar system were formed from rocky objects like asteroids, and so if we know what an asteroid is made out of, it lets us get a bit of a picture of what the solar system used to look like a long time ago.
So next news is about this another mission that just got first light a few weeks ago. The mission is called Grace FO, and the name is a bit complicated. It's the Gravity Recovery and Climate Experiment Follow-On. Is the first interferometer on space, and it's pretty cool because the way how it works. So what this mission will do will measure the change in water on Earth. So we'll measure the mass of the iceberg, we'll measure the mass of river, of lake, and so actually will be used to understand how the climate is changing on Earth. So just to explain you how this mission works, it's pretty cool. There are 2 satellites, and they're going around at the same time. And when one of the satellites will pass in front of a big mass, gravity will pull the first satellite and to go a bit faster. And the distance between them will change. And so the interferometer will measure this tiny difference in distance. And then when the second satellite will pass on the top of the mass, will then reach again the first satellite. And so measuring this small difference in distance, actually you can measure the mass of a lake, of a mountain, so it's pretty cool. And so there is also another reason why this satellite is really cool for me, because the technique that is being developed for this satellite will be used for another mission called LISA. LISA means Laser Interferometer Space Antenna. There are 3 satellites with the beam between all 3 of them. And this mission will be even cooler than GRACE, because we'll measure gravitational waves produced by the merging of supermassive black hole. It's pretty cool. We'll also measure gravitational waves from black hole and black hole merging. But even though we will have a full Astronomy on Tap about gravitational waves, let me just tell you in a couple of minutes what they are. So, in classical physics, gravitational gravity is just a force between massive objects. But for general relativity, gravity is a perturbation in the space-time. And so what's happening is that if you have a big massive object, will distort the space-time. And if you have 2 massive objects rotating in a binary system, what you will see is that they will actually produce these gravitational waves, this distortion in the space-time, and they will produce a really strong gravitational wave when they merge completely together. And so when 2 black holes merge, they produce these big gravitational waves that propagate in the space. And this distortion of the space-time will then reach Earth and stretch a bit Earth, completely. And so what you will see now is a bit exaggerating stretch of the Earth. That will be really tiny, but when the gravity wave will arrive, you will see the Earth stretching. And so what LISA will do when the gravitational wave will come, okay, not so much. I mean,
that looks scary.
So when LISA will be in space and a gravitational wave from 2 massive black holes will arrive, merging together, LISA, the distance between the satellite will change and will measure the gravitational waves from this awesome object.
That's cool. Okay, so obviously we love talking about these cool space and science things in general. That's why we're doing Astronomy on Tap. But it's also very important to remember that the people who are doing everything we just talked about and the people who do all science are human. And as the fields of physics and astronomy and science in general become more diverse as they are, it's important to take a step back and sort of realize that we need to make sure that everybody is included, not just the majority. Because it's really hard to do science if you feel under attack or worried or anxious. So this news is about the LGBT Inclusivity Best Practices Guide that came out this month, the second edition of it, which is basically an outline of how we can learn about the barriers that LGBT people face and how we can learn about how to mitigate them among our peers, our mentors, teaching, in a lot of different ways. So this is not just for people in physics and astronomy, it's for anyone who's interested in learning how your language and actions can inadvertently affect an LGBT person and how you can change yourself and your peers for the better. So if you Google this, it's online, it's available to everybody. It's a great resource.
Last news for today is that aliens finally left planet Earth. How I can say that? Well, someone made a study of, can you go to the next slide? Someone made a slide about how many people report aliens in the last years, and you clearly see that after 2014, the number of people reporting aliens decreased completely. So you can explain this in two ways. Either aliens left Earth, or aliens are really good to hide. I don't know.
I think they're hiding.
Me too.
Okay, that's astronomy in the news. Now take a break, and right. So one of the things you can do is play the trivia, which is back at the prize table with Isaiah, and you can also donate to the raffle, which is Hayabusa 2, which is awesome, or Grace FO, which is kind of awesome.
Grace.
Yeah. So if you make any donation, you can vote for one of those two things. Okay, we'll see you in 20 minutes. I was going to say it. Okay, everyone. All right, we're ready to start again. Okay, so our second speaker is Dr. Rachael Livermore, who is here all the way from University of Melbourne, Australia. She came just for us. Just kidding. She is a postdoc there, and this is her 10th location of giving a Astronomy on Tap presentation. She started the Astronomy on Tap in Austin, Texas, and our Astronomy on Tap is extremely based on that one. So we stole a lot of her material, including the intro video. Okay, so she's going to give an awesome talk about searching for the dawn of galaxies.
Thank you. So apparently my title slide got screwed up. I'm not trying to conceal my name. At the bottom there, Rachael is my Twitter handle, so if anyone's live tweeting tonight, feel free to tag me. If you're saying nice things, if you're saying mean things, maybe don't. So I'm Rachael Livermore. I currently work at the University of Melbourne in Australia, and I'm very grateful to Victoria for inviting me here tonight. I'm going to talk about searching for the dawn of galaxies, which is what I do. And luckily, Adam has laid a lot of the groundwork of what I want to talk about, so that's really helpful. And if anyone's confused, because I know Americans have this problem, yes, my accent is British. I'm originally from the UK. I worked in the US for 4 years and just moved to Australia a year ago. So galaxies. Adam talked a little bit about galaxies. We learned that there are 553 quintillion stars in the universe. That's a new word that I learned today. But what are galaxies? This is actually a really non-trivial question, because if you just look at a picture of a galaxy, how would you know what it is? And this was a real problem for many, many years. On the left there, we have a drawing that was made by a dude called Lord Rosse in 1845. And to give you an idea of what he was actually looking at, I've put the current day image of the same thing. This is M51. The one on the right was observed with the Hubble Space Telescope, but you can see that they had the basic idea of what this looked like in 1845. But the key piece of information you need to have any idea what this is how far away is it? Because it could be super close, right? And you can imagine looking at this and thinking, that's just a star in the middle, and this is maybe a disk around the star where planets are forming. That's what a lot of people thought this was. Or it could be a thing that is super far away, that is like our entire Milky Way, but really far away. They would call that an island universe. And for many, many, many years, there was a huge debate between these two camps. A lot of people didn't like thinking that this was a complete island universe because that would make the universe absurdly huge. It's much more comfortable to think that the Milky Way is the entire universe and this is just a thing that happens to live in it. So there were a lot of arguments going on about this, and it culminated in 1920 with a thing called the Great Debate between two old white dudes who had a big production of an argument where there was no resolution, but somehow they get mentioned in every textbook, and I'm deliberately not having a slide about them tonight because it was stupid, because they didn't come to a resolution. The only reason we were able to come to any kind of resolution about this is because of Henrietta Leavitt, who was what was known as a computer working at Harvard College Observatory. And at the time, women were employed as computers to do all these very menial computational tasks, back in the days when computation was seen as a secretarial duty and given to women. And her job in particular was to catalog variable stars. She was looking at some particular stars in the Large Magellanic Cloud called Cepheid variables. And this is, unfortunately, the credits dropped off, but this is from a really cool book about her. It's a picture book for kids. I highly recommend it. And on the top, you can get an idea of what these stars look like. They're stars that brighten and dim in a regular pattern over time. And if you plot their brightness as a function of time, it looks kind of like this. Underneath, it goes up, it comes down, it goes up, it comes down. Very, very regular pattern. And as you know, if you've ever done a very menial repetitive task, you start to notice patterns that maybe other people haven't noticed. And what she noticed was that there was a very clear link between how often this pattern repeated and how bright the star was. In fact, you can plot those things against each other and you get something like this, where along the x-axis here, we have the period of variability. So this is just the gap between the bright points of this repeating pattern. And on the y-axis, we have the brightness of the star. And you can see very, very clear relation. Now, it's important that these stars were all in the Large Magellanic Cloud. So when you say one star is brighter than another, we know that they're all at the same distance because they're within the same object. And therefore, it is actually brighter. It's not just that it's closer to us. So this is a really, really important relation, because measuring how bright something is super hard. You have to know how far away it is. But measuring a repeating pattern and telling the time difference between these repeating patterns is super easy. And if you have a plot like this, you can measure the period of variability, go up to your line, and read off the actual luminosity. So this is really, really important. Once you know how bright something actually is, and you can obviously measure how bright it appears to be to you, you now know how far away it is. This is extremely important. This was discovered in around 1912, and it was put to use by Edwin Hubble around a decade later, when he found one of these Cepheid variable stars in the Andromeda galaxy. This is our closest big galaxy, similar size to the Milky Way. No one knew how far it was. It was just known as another of these spiral nebulae. Is it an island universe? Is it just a star in our galaxy? Hubble used Leavitt's law to look at one of these Cepheid variable stars and work out how far away it was. And he was able to calculate that it was 900,000 light years away. Now, if there are any super nerds in the audience, which I'm assuming there are, you're probably thinking, well, that's not right. We actually know today it's about 2.5 million light years away, but to astronomers, that's the same. It's the correct order of magnitude. The Milky Way is about 100,000 light years across. So this put Andromeda way, way, way outside the Milky Way. And this is really important because it means it is indeed an island universe, which suggests that all of these spiral nebulae are in fact island universes. And therefore, the universe is way bigger than anyone thought it could have been. Now, Hubble, of course, took this further and combined these distance measurements he was now able to take with measurements of how fast galaxies are moving, either towards or away from us. And you might expect that that would be kind of random. Some galaxies would come towards us, some would go away. What he found was this, which was not expected at all. Every galaxy is moving away from us, pretty much. Andromeda is actually an exception. It's very close and it's coming towards us. Other than that, galaxies are moving away, and the farther away they are, the faster they're moving away from us. So you get this very nice relation. The more distant something is, the faster it's moving away. And this has huge implications because it turns out the only way you can really explain this is if the entire universe is expanding. A lot of people get a little caught up on this and think, well, if everything's moving away from us, does that mean we're at the center of the universe? So a quick explanation of why that's not the case. Picture a balloon. Start with your uninflated balloon and draw galaxies on it. I've seen a lot of people do this exercise and they draw stars. That's incorrect. You want to draw galaxies. And now inflate the balloon and watch one of your galaxies as the balloon inflates. You'll notice that all of the other galaxies appear to move away from that one. And it doesn't matter which galaxy you pick, all the other galaxies will move away from it. Now, if you think about this too hard, it will fall apart. Because in this analogy, the entire universe is just the surface of the balloon, which is two-dimensional. And there is a center of the expansion, but it's in that third dimension that doesn't exist. So don't try and think about it too hard. It's an analogy. Now, there's a really useful implication of this expansion of the universe, which is if the universe is expanding, and therefore everything appears to move away from us, it's not really moving away from us, it's that the space in between is getting bigger, but, same effect. If everything appears to be moving away from us, the light appears redder. And the reason for that is very similar to the Doppler shift that we hear in sound. If you have us observing on Earth over here, and we have a galaxy emitting some light, and we're looking at a particular feature in the light it's emitting, which is this black line. If everything's stationary, that black line will stay where it was when it left the galaxy, and it will look green. If this galaxy moves away from us, all these light rays are the light waves are being spread out. So just as a car moving away from you has a lower pitch than if it's stationary, this black line now moves towards the red end. And astronomers use the word color in a really confusing way. Yellow is redder than green. And conversely, if that galaxy is moving towards us, that black line is going to move towards the blue end, and so it's greener than it was before. But for our purposes, it's always this. The galaxy's moving away, stuff looks redder the further away it is. We call this redshift. And the reason this is really useful is, again, because distance is really hard to measure. Distance depends on being able to look at an individual star to figure out how far away it is. And you very quickly run into the problem as you go further away that you can't see those individual stars anymore, so you need a new method to work out the distance. And this redshift is what allows us to do this. We can now say, based on the calibration we've done and things nearby to us where we can see those stars, that we know how fast the universe is expanding, therefore we can look at how much redder things look than they should, therefore that's how far away from us they're moving, and therefore we know how far away from us it is. So this is now how we measure distance, and this is why when people say redshift, that's the same as distance, and it's also the same as time, because the further away something is, the further back in time we're seeing it. So I'll use interchangeably distance and a period of time, and it all means the same thing. So for many, many years, the things we knew of that were the most distant in the universe were things like this. This is a quasar. They were discovered in around the 1950s. They're super bright, and they were really confusing. They're called quasars because they were known as quasi-stellar objects, because they kind of look like stars. They're just really bright points in the sky. Of course, this does not look like a bright point in the sky. Normally, you see them as just a single bright point in the sky. But they had this redshift, which implied they were really, really far away. But this couldn't be right, because if you take something that's super bright and you say it's really, really far away, then if you got up close, it would have to be insanely bright. And there was no mechanism anyone knew of that could produce something quite that bright. Until models in around the 1960s and 70s figured out accretion disks. And it turns out if you take a black hole, which has a really, really deep gravitational pull, and you put stuff in the gravity of a black hole, that stuff will kind of orbit around it, kind of like water swirling into a plug hole. You don't call them plug holes in America. That thing at drain, thank you. Sorry. And as that stuff swirls around and falls into the black hole, it's rubbing against each other, and that generates friction, which generates heat. These things get incredibly hot and emit really, really high energy radiation, things like X-rays. And this is what a quasar is. It's a black hole, stuff falling into it, really, really hot, and therefore really bright. And they are indeed super far away. But that's kind of boring, to say that the only things we know of in the very, very distant universe, and therefore far back in time, are these really, really extreme objects. I find that kind of boring. That's because I work on galaxies. So how do you find normal galaxies that are far away? It's really hard, and it depends entirely on the technology that you're using to discover them. Everything we do in astronomy is so incredibly dependent on the technology we have available. And things changed dramatically in the 1980s. Does anyone know what happened in the 1980s? Digital cameras. So charged coupled devices, or CCDs, were invented actually completely by accident. I forget what they were trying to do, but there were some guys experimenting at Bell Labs, and they invented this thing that turned out to be really sensitive to light, which was not what they wanted. But astronomers went, yoink, we'll have that. And so CCDs were fitted to cameras. And I want to show you how much of a difference this makes. It's really quite incredible. This is an old image of what? Does anyone know? It's really hard. It's actually the Horsehead Nebula. So this tiny, tiny dark shape here, you can just see a very faint shadow there, is this thing. So two differences. The top one is taken with a photographic plate, much wider field of view, but also much less sensitive. This is an image taken actually in the early 90s with the Canada-France-Hawaii telescope, which is in Hawaii, of the same Horsehead Nebula. You can see so much more detail. So we now know this is a big cloud of gas and dust where new stars are being formed. And here's a more modern image taken in 2011, I believe this one was, also with the Canada-France-Hawaii telescope. So this is how much of a difference these new cameras have made to astronomy. It's pretty amazing, and also pretty cool that just in our quest to understand the universe, we developed something that we now all have in our cell phones. So next time you take a selfie, you can thank astronomy for that. Now, another really cool thing was going on around this time. Because we had these new sensitive images, we were able to detect things we'd never detected before. And one of them was gravitationally lensed galaxies, which I'm going to talk about because that's what I work on. It's also what is featured on my dress. I like to make dresses out of my science, so that when people see me at conferences and say, oh, I'm really sorry I missed your talk, I can say, that's fine, I can give it to you now. So I'm going to explain gravitational lensing because it's super cool, and I understand you're going to have a full talk on it in a few months, so I won't linger on it too long. This comes out of general relativity. Don't fall asleep. General relativity is so cool. What general relativity tells us is that space is not an empty arena in which stuff happens. If you imagine empty space, you can picture it as a two-dimensional sheet. Again, we're analogizing the universe as two-dimensional. It's easier. And you can move in a straight line through flat space. If we introduce mass curves space, and now anything moving through that space follows a curved path. And that thing can be another thing that has mass. Say this is the sun, this could be the Earth. Hopefully it won't follow that trajectory, but this is why the Earth stays in orbit. It thinks it's going in a straight line, the space is curved, so it keeps going around the sun. But it could also be light. And if light moves past anything with mass, its path gets curved, and so the image will get distorted. And when this was first discovered, Einstein published it in 1915, so just over 100 years ago. This lensing effect, where the mass is acting like a lens bending light, was thought of as really just an oddity, but maybe kind of useful for proving that general relativity was real. And it was actually the way that general relativity was proven real. Imagine you have a random field of stars. This is, I'm just going to warn you, the best use of PowerPoint animation you will ever see. I'm secretly an artist. So we have here a random assortment of stars. Now, normally when you look at stars, you do so at night, which means if the sun is here and I'm the Earth, we're going to look that way. But imagine we wait 6 months, the Earth goes around the sun, we're now on the other side of the sun, and we look at those same stars. So now the sun is in between, and because of this lensing effect, those stars appear in a different position. They actually all move outwards from the sun. Now there's a reason we don't do this all the time. You can't see stars past the sun because that's daytime, and it's really hard to see stars during the day. But when can you see stars during the day? An eclipse. Who saw the total eclipse last year? Yay! Obviously, this is a room full of astronomy nerds. Of course everyone did. Yeah, I actually helped run an event out in South Carolina for it last year, and it was amazing. So during an eclipse, we move the moon in front of the sun, block out that light. Now we can see these stars, and we can see that they're in a different position than they would have been if we saw them at night. So this was actually done in 1919. A small island off the west coast of Africa, a team led by Eddington actually measured some stars during an eclipse, found out they were in a different position, and therefore proved general relativity. And Einstein became a celebrity, and this is basically the reason you've heard of him, even though it's not why he won a Nobel Prize. But this turns out to also be really useful. So let's pretend that the Whirlpool galaxy here is super far away, and we're observing it with Hubble. And normally, when things give out light, the light goes in all directions. And I'm only showing 3 directions, but there's a lot more than that. And only some of that light, a very small portion of it, is going to fall on our telescope. If we now introduce mass in the middle, some of this light gets bent, and it acts just like a lens in focusing the light, so that in my super technical diagram here, we now have 3 lines going into our telescope instead of 1, which equals more light. And this is really useful because more light from our faraway galaxy means we can see much, much fainter galaxies than we can normally. So this is really cool. And the reason this image is in the middle is that is a cluster of galaxies. Galaxy clusters are the most massive things in the universe. They're mostly dark matter, and they bend light a lot, and therefore do a lot of this lensing effect. And how is this relevant to CCDs? Well, this was actually theorized back in the 1930s by Fritz Zwicky when he was at Caltech, and completely ignored for about 50 years, because there was no way we would ever actually be able to detect anything like that. But then bring in CCDs in the 1980s, and people immediately found this. This was discovered in 1986. This image is not from 1986. This is from the Hubble Space Telescope. This is Abell 370 is the name of the galaxy cluster. All the big orange things you see here are galaxies in the cluster, which I don't care about. But this gigantic red streak here, which we call the red dragon, is a faraway galaxy way behind the cluster, that's been lensed by the mass of the cluster, and it gets stretched into this gigantic arc shape, which is super cool, and it allows us to see so much more detail inside the galaxy than we can normally. Now, as I said, this was discovered in 1986, so the original image was not this shiny. But anyone know what happened in 1990? Hubble, yeah. The Hubble Space Telescope completely revolutionized this entire field. And in 1997, it observed another galaxy cluster called MS1358. I'm really sorry for these names. Astronomers should not be allowed to name anything. So this is the galaxy cluster, MS1358. We're doing a little fly around it now, but I don't care about the galaxy cluster. I care about a thing that happened to lie directly behind that cluster, which is this. Now that bright thing in the middle is just a cluster galaxy. I don't care about that. But that big streak there, that is an extremely distant galaxy. This is seen just a couple of billion years after the Big Bang. And it's gravitationally lensed, which makes it brighter. And so in 1997, that thing became the first normal galaxy that was not a quasar to hold the distance record. This was the most distant thing we had ever discovered as of 1997. And it features in my PhD thesis. It's a really cool galaxy. Now, the great thing about Hubble is that it's actually really close to us. It's only about 350 kilometers up from the surface of the Earth. And so we can send people up to fix it. Because these days, although it's still our best telescope, it's 1980s technology, it's kind of old-fashioned, but we've been able to go up and surface it and fit new cameras to it. And so this happened in 2009. If anyone saw the IMAX movie, Hubble 3D, which I highly recommend, it's so cool, it covered this servicing mission in 2009, which installed the Wide Field Camera 3. And the Wide Field Camera 3 is a boring name, again, but the coolest instrument in astronomy because it gave us this image. This is the Hubble Ultra Deep Field. It had been observed before, but Wide Field Camera 3 gave us much, much more sensitive, very red imaging. Now, this image might look kind of big, but just to put this into perspective, if you take a grain of sand and hold it out at arm's length, that grain of sand would completely cover this patch of sky. This is a teeny tiny patch of sky, and there are around 10,000 galaxies in it. So imagine multiplying your grain of sand over the entire sky. That's how you get to 553 quintillion stars. There's a lot of stuff in the universe. Now, what's really important is that Wide Field Camera 3 looks in the infrared. And I mentioned the universe is expanding, things look redder. Once you get to these very, very distant things, all of the light kind of falls out of the optical range of the spectrum, which is what our eyes can see, and we need to be able to see it in infrared. So when we actually look at distant galaxies, we look in black and white at just a specific wavelength range using filters on our camera. So these are the filters we use on the Hubble Space Telescope. And so we'll observe the same galaxy 6 times. And if we look at a galaxy that we're seeing a billion years after the Big Bang, it looks like this. We can see lots of light in the infrared, and we can see nothing in the optical. And this is really useful because this tells us how much that light has been shifted towards the red, and therefore how redshifted it is and how far away it is. Which is why we spend an awful lot of time using the most expensive telescope ever to take those images with nothing in them. And you can actually go even further away. The limit of what we can do with the Hubble Space Telescope is going 500 million years after the Big Bang. This is when the universe was only like 5% of its current age. And we now get this solitary dot, and the very reddest image we take, and a whole lot of nothing. So this is, by definition, the furthest away we can see with Hubble. So let's say we want to look even further away. We want to go more than 500 million years closer to the Big Bang. What do we need? We need a new telescope. And this is something that's in progress. This is a bit of a sore spot for me right now. This is the James Webb Space Telescope. which was originally conceived of right around the time Hubble launched in the early 1990s, and was scheduled to launch in 2007. I've got to tell you, this is an artist's conception. It doesn't currently exist. That's not true. It exists. I've seen it. It's at Northrop Grumman in Southern California. It's supposed to be in space. Hopefully it will get to space one day. They're currently saying 2021. I'm not staking my life on that. We'll see. But this is going to be amazing for two reasons. First of all, it's big. Now, telescopes are essentially buckets for collecting light. And there's two ways to collect more light in your bucket. You can leave your bucket out for a really long time. Well, that was the Hubble Ultra Deep Field. We've done that. Or you can get a bigger bucket. So this is our bigger bucket. You can see there how it compares to Hubble. It's much bigger. Spitzer is the current infrared telescope that's up in space. And you can see how pathetic it looks next to James Webb. The other thing that makes James Webb really cool is it looks much further into the infrared than Hubble. So if we look at our galaxy 500 million years after the Big Bang, where we had just this one detection, if we add in Webb, we get all these other detections and much redder wavelengths, which means we can go further, right? 370 million years after the Big Bang, we still get all of these detections. Even 270 million years after the Big Bang, if you think these numbers are random, it's because of weird units we use in astronomy, but we still get a detection in all of these bands of Webb. So this is going to be really, really amazing. It's going to let us go way further back than we've ever seen before, and also in much more detail than we've ever seen before. So I really like playing with the Whirlpool galaxy for some reason and pretending it's far away. So let's pretend the Whirlpool galaxy is so far away that we see it in the first couple of 100 million years of the universe. And we want to observe it in the ultraviolet, which is where all these hot, young, new stars live. This is what it would look like. But what we really want is to see it in the optical range of the spectrum, which again has been shifted out to the infrared. And we currently have to do that with Spitzer. And I went backwards. I knew I was going to trip up. It looks like this. That's not good. If we add in the Webb telescope, it's going to look like this. So this is going to completely revolutionize this field, and it's going to be really amazing. And so, in conclusion, if it ever happens, JWST is going to be awesome. Thank you.
All right, thank you, Rachel. We got a million questions for you. We chose 4.
Okay, the first question is, what is driving the Andromeda Galaxy toward the Milky Way?
Oh, what is driving the Andromeda Galaxy towards the Milky Way? Gravity. So gravity has a tendency to pull everything together, and the expansion of the universe pulls things apart. But when things are very close together, gravity dominates. So because the Andromeda Galaxy is much closer to us, gravity is more important than the expansion of the universe, and therefore it's coming towards us.
So you said that when something is farther away, it changes the spectrum of a galaxy. How do you know the difference between something being redshifted or something being farther away and something having a different composition?
Oh, that's actually a really good question, and it's actually not trivial. So the correct way you do it is spectra have patterns. So we take an element that we know really well, like hydrogen, and we say hydrogen has this really distinctive pattern where you see an emission line here, an emission line here, and an emission line here. Every galaxy has hydrogen in it, so it's a really easy one to look at. And you see that distinct pattern, and if you see that, but it's like spread out a bit, it has to still be hydrogen, and therefore you can work out how much it's been shifted. Now, the reality of what we do is we can't see all these multiple lines, especially as we get to really distant galaxies. Things have been redshifted so much that most of the lines we would look at have fallen off our cameras. So we have one single emission line, which we call Lyman alpha. It's a particular hydrogen emission line. and we see this one thing, and we say, it's Lyman Alpha, this is a really far away galaxy, and we fight over it a lot.
Okay. Next question. Okay. What are these things coming out from the quasar?
Oh, yeah. You know what? I could give an entire talk just about quasars. You should do that. They're really cool. So as you get stuff falling into the black hole, it will shoot energy out, like both sides, for reasons that are complicated and can fill an entire talk. So you get these jets coming out of the black hole, which you can observe, and they're real things, and they're really cool. But it's because of the energy of stuff as it's falling into the black hole.
That's a teaser. We'll have a whole talk about that. So not all the images that you showed have only wavelengths in human vision. So for the images that don't have wavelengths in human vision, how do you see them? Like how do you make those into images?
Okay, so whenever you make a color image, you basically take 3 black and white images, and you assign one as red, one as green, and one as blue. So if you're trying to replicate human vision, you would take 3 black and white images from wavelengths that humans can see, and then the bluest one would be blue, the middle one would be green, and the reddest one would be red. So for infrared, we do the same thing. We just assign those 3 colors to 3 images and reproduce something as close to what we would see as we can. And I don't really like it when people call it false color, because if you look at an optical image, that's also false color. If you've ever looked through an actual telescope at a galaxy, it just looks like a fuzzy white thing, because our eyes are not that sensitive to low surface brightness colors. The bits of your eye that are most sensitive to low surface brightness are just register black and white, so things just look fuzzy and white. And when we make these pretty images with Hubble, Hubble is way more sensitive than your eyes, and so the colors are already kind of fake.
Great, thank you. That's all the questions. Let's thank Rachael again.
Okay.
All right, so we have a trivia and raffle winner, but before we do that, I'm going to have the person in charge of Capital Science Communicators come up and do a short little announcement really fast. This is Nick Gray.
Hi, everybody. Thank you, Victoria. I appreciate the opportunity to let you in on a little announcement. For those of you who don't know, Capital Science Communicators is a social and professional network for anybody whose professional lives intersect with the world of SciComm. So if you're a scientist who wants to better communicate your science, learn how to do that. We put on workshops to help you do that. If you're a communicator, a writer, a journalist, a creative of some sort that wants to better communicate science that you don't really know about, we help you out there as well. Some of the other services that we provide to the community are also science tours. We do behind-the-scenes tours, a lot of things in the region that maybe you didn't know about. So we just recently did a tour of Rancho Seco. It's an old SMUD decommissioned nuclear plant that's now a vast solar array. We've been behind the scenes at the Sacramento Zoo. We went to Cal ISO, which is like ground zero mission control for most of the electricity distribution in this state. Really cool. We got to see like the big board. It was really cool. Anyway, so my announcement tonight though is I'm happy to tell you that we are going international. We're going abroad with our next tour. We're going to Costa Rica. And I'm inviting everybody in the room to go with us. So we are going to Costa Rica, conveniently timed for the spring break of UC Davis, the last week of March. And it's an all-ages trip, family-friendly, and it's science-focused. So we're going to be spending an entire day at a biological research station in Costa Rica. We're going to be spending time on the Pacific coast with Oliver Ridley sea turtles. We are doing bat master classes. We are doing chocolate and coffee and some ag stuff. And then we mix in a nice little bit of leisure and fun as well. You're going to get to choose from some adventure activities like whitewater rafting and horseback riding and zip lining. We're also spending some time in Arenal, the volcano, soaking up the hot springs around Arenal. So if you want to know more, you can go to our website, capsicom.org, or I'll be hanging around. Feel free to chat me up about it. And we'd love to take everybody with us. Oh, and the other thing, we're taking a couple of scientists, local scientists who have experience, research interest in that area to go along with us to give us a little local flavor, from the Sacramento region. So join us. Thank you.
And the trip is free for everyone. Yay!
Thank you, Nick. Yeah, go talk to him. He's super nice, very friendly. Okay, so now we have the trivia and raffle winners. So we'll say the trivia winner first. I think maybe 4 people or 5 people got them all right. So again, it was random. Apparently, we need to make these harder. Okay, but the winner is, I think, Zane Moore. Okay, good. You need to work on your handwriting.
Okay. And for the raffle, oh, I like more the other one. Come on. The graceful.
Mine won.
Okay. How we do that?
Stump it out.
Okay.
There you go.
Okay. So the winner is number 42. No. 403039.
Oh, good.
Robert?
Yay. Congratulations.
Okay.
Okay, so. Right. So, Zane, you can choose between the Chewbacca mask and the 30-meter telescope mug.
What you will choose?
Oh.
Which one you take?
So, the raffle winner, what's your name? Robert can choose from the Galileoscope and the Chewbacca mask. Awesome. Yay. Okay.
Okay, thanks for coming. I just want to mention that the next Astronomy on Tap will be in September. We skip August, so the third Thursday of September, we will be here.
Yep. You can come to Studwork in August, but we won't be here. Okay, thank you guys.
Thank you.
All right, bye. Yeah. Good luck with the stuff. Yeah.